This is Lesson 60 from Saxon Algebra 1. It starts in Lesson 60 talking about geometric solids. And they referred many lessons ago to geometric solids and defined them as a geometric figure that has three dimensions. So here are some examples, and I'm going to use some illustrations straight from your textbook so that we are using the exact same thing and we can look at the same pictures together. So first we're going to start right here with the right triangular prism. As you can see, if you look at the front of it, you actually see a square or a rectangle shape there. But what we're really focusing on to identify it as a triangular prism is looking at the top and bottom footprint of it and seeing that from there may be some rectangular sides on each side of it, but the figure itself has triangles on the top and bottom, and then it is just stretched out in a more three-dimensional way. So it's almost like you took a triangle here and then just stacked a bunch of, imagine if this was a piece of pizza, for example, and you just stacked layers and more pieces of pizza on top of each other until it came up to be a three-dimensional shape. So the next one is the right circular cylinder. So the circle is the shape of the base footprint and the top, and then we call it a cylinder because it stretches down in a three-dimensional way. Then we have another one. This next one is the regular square pyramid. Again, when we identify the shape of the geometric solid, we want to focus in on the footprint, because when you look at this pyramid, you can see some triangles are involved, but we're focusing on what is in the footprint of that shape. And because that starts as a square and then goes to the top in a pyramid formation up to one point, that's what makes it a pyramid. Then the next one is the right circular cone. And again, it's circular because when we focus on the base or the footprint of that, it's a circle. And it makes a cone shape because it comes up to a point. And then the last one is a sphere. And the way I took this picture in the textbook, the sphere almost looks a little bit like an oval. But it's important to look in your textbook. This looks a lot flatter and more perfectly round shape in your textbook. So again, I'll kind of draw it to the side here too, just to remind us that this looks a little cut off on the side. But a sphere has a circle in the middle, and then it has a radius that comes out from the center to touch all the sides, and it's equal. That radius is the same from the center to any point on the outside of the sphere. So these geometric solids are easy to identify and recognize once we learn all their names, but they're not necessarily easy to define mathematically. In this book, they're not going to give the formal definitions of these geometric solids since they are rather complicated. Instead, we're going to give what mathematicians would consider informal definitions. So in this lesson, we're going to re-examine prisms and cylinders. In later lessons, we'll talk about pyramids and cones. So they're saying for this lesson, they're going to focus on the prism and the cylinder, and later we're going to do these other three. But for this lesson, we're not going to do these three. So we're going to focus on the prisms and the cylinders. So here we go, talking about prisms and cylinders. A prism is a geometric solid where two faces, which are called the bases, are identical and parallel polygons, and where the other faces are parallelograms, or called lateral faces. So a prism, when we looked up here, remember we had our right triangular prism. What they're saying is if you have a geometric solid, So again, we're going to do like a little piece of pizza here. And this is one face of it, or what we would call a base. And if we had another face, which they still often call another base, even though it's on the top. So these must be identical and parallel to one another, meaning it's not, neither of them are tipping in any way. They're exactly the same distance at every point from one another. And then the spots between them, if I have this coming down, this coming down here, so the faces between them, we have this kind of back face along there, and then the back one I'll kind of do in yellow there, and then there's sort of a front face across this. So there's three faces or lateral faces of this, and these are all parallelograms. The lateral faces intersect in segments called the lateral edges. So in this one, this is a lateral edge where the red side meets the green side. Here's another lateral edge where the green side meets the back yellow side. And then back here, kind of in a dashed line, is a lateral edge on the back that you can't really see through it, but it's where the red and the yellow sides meet. So this particular right triangular prism has three lateral faces, and they intersect at three lateral edges of this prism. The altitude of a prism, I'm going to underline that word. The altitude of a prism is the perpendicular segment joining the planes of the bases. So the perpendicular segment of the planes joining the bases. So in the illustration we were just using up here, because I have this standing straight up where it's exactly the same height on each one and it's not tipping in any way, my lateral edges are the same as my altitude. Because again, the altitude is the perpendicular segment, meaning it's kind of at a right angle to the ground there. It's the perpendicular segment between the two bases. Now, if you look at their illustration down here, they have a prism. It's not a triangular prism this time. It looks like it has 1, 2, 3, 4, 5 sides. And this prism, they have an identical one up here, but it's shifted over. It's still the same distance from the base. It's not tilted, but it's shifted a little to the right, which makes this prism sort of leaning a little bit more. So they're reminding us that these are the lateral edges, like in between all of these lateral faces. But because they're tipping, they're a little bit longer than the altitude. The altitude is actually the measurement between the plane that the base is sitting on and the plane the upper base reaches up to. So the altitude is the height of the prism. Again, because this prism is sort of leaning, we can't use the lateral edges to necessarily guide that as the height. The height needs to be the actual height from base to base. And in this one on the right, it's showing one that's standing more upright. So the altitude of this one looks like it would be the same as the length of the lateral edges. So again, they're going to review here. The prism on the right is a special type of prism. It's called a right prism. By calling it a right prism, that is pointing out and defining for us the straightness I was just talking about, where the altitude will be the same as the lateral edge. So it is standing where every lateral edge is at a right angle to the plane. Oops, I should have made a straighter line there. I apologize. Let me do my eraser. So here it's at a 90-degree angle. Each of these lateral edges are at 90 degrees to the base that it's sitting on. So we know that these are perfectly straight up and down. We would call this just a regular prism on the left, but this is a right prism because the lateral edges are also the altitude. in this book, they're going to confine their discussion of prisms to right prisms. So they're not going to talk a lot about these leaning ones where they're tricking you with a different altitude to the lateral edge. So we're going to focus on straight up and down prisms in this text. Prisms are classified and named according to the shape of their bases. Here we show 4 examples. First, we have a right triangular prism, and again, to name it, this triangular piece is because of the base shape. Since the bases are triangles, it is a right triangular prism. The next one is a right rectangular prism, because again, we need to look at this base shape to decide that. And because it's a rectangular, and because the edges are straight up and down, it's a right rectangular prism. And the next one is a trapezoidal prism, where the base of it, I'm going to draw another, I'll just draw a trapezoid so we can remember what those look like. This should look a little more, let me fix it so this looks, hopefully you get the idea of it. So this is the trapezoid here on the top and the bottom. And then the last one, switch to another color, is a right pentagonal prism. That's like the examples we had above, where there are 5 sides, like a pentagon. So the penta is our signal. That means 5 sides. So that's just a review of what we name each of these. Again, don't look at these lateral faces to decide what to name it, because the lateral faces often all look like a rectangle. So again, look at the base when you're deciding how to name your shape. The next piece of the lesson talks about cylinders. A cylinder is like a prism, except that its bases are closed curves instead of polygons. So there aren't the hard shapes with the edges like we had with triangles or pentagons. Instead, we have curved polygons, or instead of polygons, excuse me. So the curved surface between the bases is called the lateral surface. So we have here a base, which is a circle. We have a base of a circle at the top. And then the parts in between this whole surface that I'm sort of shading in, kind of coming along the outside, it's curved because it follows the shape of those circles, and that's the lateral surface of the cylinder. The segment joining the centers of the bases is called the axis of the cylinder. So I'm going to erase my shading so I can point out the axis to you. So the axis is taking sort of the point in the center of each of the circles and joining it with a line that connects them, a straight line in between the centers of each of those circles. So that is the axis of the cylinder. The altitude of a cylinder is a perpendicular segment joining the planes. So like we talked about the altitude with the prisms, the altitude also is the distance between the plane that each of the bases is sitting on. Then the length of the altitude is the height of our cylinder. So in this one, this is a regular cylinder, but it happens to be leaning. So this lateral surface is a little bit longer of a distance between the two than the altitude, because the altitude is straight up and down between those planes. If you look to the right, we have a right cylinder. A right cylinder means that the lateral surface is at a right angle to the bases. So a 90-degree angle. And if you note, because of that, the axis is also the altitude or the height of our cylinder. And I think they're going to follow the same pattern and use more right cylinders rather than like leaning cylinders as they keep going through this text. So moving on with the lesson, cylinders are classified and named according to the shape of their bases, just like prisms were. And the right cylinder that you see here in this picture is a right circular cylinder. Again, we name it, that circular part is because there's a circle for each of those bases. In this book, we're going to define our discussion of cylinders to right circular cylinders. So they won't be doing like oval cylinders in this text. They're going to focus on ones that have a perfect circle at the top and bottom, and that'll make it a lot clearer and easier to work with, actually. Now we're going to talk about finding the volume of these shapes of either prisms or cylinders. Again, a prism, here's a rectangular prism. I'm going to kind of draw to this side here. It's not going to be perfect. So this is an example of a prism. And again, a cylinder has rounded edges. Oops. So picture those being perfect circles. So we are going to find the volume of both of these types of objects. So first, it's important to remember what volume is. And it's sort of the amount that it takes to fill up the inside. So if you imagine your prism or cylinder as a big empty container, and you're about to pour some kind of liquid in it, let's just say you're going to fill it with water. So we'd want to know how much water, or how much sand, if you're talking about maybe a more solid object rather than liquid, but how much it would take to fill that. That's the volume. And to calculate the volume of a prism, it's pretty simple. We just need to multiply the area of the base and multiply it by the height. So they're just defining that here. The volume of a prism or cylinder is equal to the area of the base times the height. So I would write that in more mathematical terms as V. We often use a capital V for volume. The volume equals the area. And since we're talking about, it's not just any area, it's the area of the base. I'm going to write base really small, kind of as a subscript of area. And we're going to multiply that by the height. And we usually use a lowercase h to represent height. So we're going to do an example. We'll read this one together. The area of a base of a right pentagonal prism, and they drew it over here, is 28 centimeters squared. So they're telling you that the area of the base of that prism is 28 centimeters squared. And the length of a lateral edge is 10 centimeters. So that means if this is a lateral edge, they're saying that that's 10 centimeters tall. Find the volume of this right pentagonal prism. So when they called it a right pentagonal prism, they were sticking to what they told us, that they're going to just use right prisms. And that tells us that since they told us the length of this lateral edge, we also know that that is the actual height of this prism. So because the volume will equal the area of the base times the height, we just plug those in. So the volume will equal 28 centimeters squared because they told us that was the area of the base. And then they told us the height is 10 centimeters. So when we multiply 28 times 10, we get 280. And then we also need to make sure to multiply our units. When we multiply centimeters squared with just another centimeter, it becomes centimeters cubed. It's very important anytime you're talking about volume that your units work out to be cubic units, because we're talking about three-dimensional objects here when we're finding volume. Next, they talk about finding the surface area of prisms and cylinders. Now, this is a lot to have all in one lesson. This is a big lesson that you might even want to watch again. But there's a big difference between the volume and the surface area of an object. If they're asking for the volume like we just talked about, you're filling the inside, like you're just filling up the contents of that shape. But the surface area is just measuring what's really on the surface. You're not putting anything inside. You're just measuring the area of the base at the bottom, the base at the top, and then all those lateral surfaces around the side. So the lateral surface area of a prism or cylinder, we define it as the area of all external surfaces, except the bases. So when we're going to start with just the lateral surface area, we're just going to start with the outer surfaces, the external surfaces, not including the top and the bottom base. Okay, unfortunately, they're telling us there's no simple way of computing the lateral surface areas of prisms or cylinders unless they are right prisms and right cylinders, which again is why they use them in this textbook. If they're leaning, it gets very complicated how we figure those out. But again, because they're straight up and down, it's going to be a lot more straightforward. So the lateral surface area of right prisms and right cylinders is equal to the perimeter of the base times the height. So, to find the surface area of a prism or a cylinder, we add the areas of the bases to the lateral surface area. So we're just going to start with the lateral surface area, and we'll throw in an example here. So here's our example. We want to find the lateral surface area of this right prism. And it tells us the bases are regular pentagons, so we know that. And the dimensions are in meters. So they're writing numbers here, but they usually tell you in words in the problem what the units are, and they're meters. So to do this, we need to imagine this. And again, we're just starting, we're not doing the bases, we're just doing all these sides, and we know that there are 5 sides. So what they did here in this picture, look closely at this. Imagine they took off the top and bottom, so there's nothing on top and bottom, there's no bases there right now. And imagine they took a pair of scissors and just cut it right here and laid it out flat, so that all those 5 sides are laid out flat. And this is a picture of it laid out flat. So this side right here, this square, or excuse me, a rectangle, is this rectangle. And then as you go around, or imagine they cut it right here. And so this rectangle is representing this rectangle, and so on, until it lays out and you have all 5 rectangles of this prism. So we're using the units they gave us in the problem, and they put the 15 showing the height. So that means the height from top to bottom is 15 meters. And it means 8 units are the base of each of these rectangles. So we have 8, 8, 8, 8, and 8 to make the whole way around. And so if we're looking at the perimeter of that pentagon, if we added all those 8s together, we get the perimeter of that base. So that's the first thing we're going to focus on, is adding those together. 8 plus 8 plus 8 plus 8 plus 8 equals 40 meters. So that's the distance around the base. And then the height of the rectangle was told to us as 15. And because this is the formula we're using, lateral surface area equals the perimeter of the base times the height. So the perimeter of the base we found by adding those 4 8s together. The height was given to us. So when we multiply 40 and 15, we get 600. And then when we multiply the units, meters times meters, we get meters squared. Because again, we're not finding the volume here. We're finding the lateral surface area. And area always ends up with their units squared. So then you know you're searching for the area. So that's the surface area all the way around that shape. If later they want to ask you the surface area of the whole thing, you would find the area of the top and the bottom, which are the bases, and then add that on to the lateral area. But that will be coming down the road. So right now they're just going to have you find the lateral surface area, meaning just the surface area of all the pieces on the sides. So if they were having you find the surface area of a more here, we would just have 3 sides. We would have this back yellow side, and this back side in green, and then this front side. So we would have those where we would add the area of the front side to the area of the green side to the area of the yellow side. So when you're finding the lateral surface area of a triangular prism, you would do the same thing. They would give you a height. Let's say they told you that this is 5 units tall. Then you would have a 5 here. And then they would have to tell you what each of the sides equals. Maybe this front side was 7 units. This back side in green maybe is 4 units. And the yellow side along here, let's say, is 3 units. So if this was 3 units, this is 4, and this was 7, we would add these together, 7 plus 4 plus 3, and that would be the perimeter of our base. 7, 3, and 4 would be 14. And then we would use this same formula for the lateral surface area, and let's take that out. So the lateral surface area would be the perimeter of the base, which we found up here is 14, times the height, which we decided in this one is 5. And let's say in this one we're going to say we're dealing in centimeters. So the lateral surface area will be 14 times 5, which is 70. And because we're talking about 14 centimeters and 5 centimeters, when those multiply, they become centimeters squared. So that's just another illustration to show you don't need to just be using one that started out as a pentagon and has 5 sides. You might be just dealing with 3 sides if it started as a triangle. So let me know if you have any questions coming up in this lesson set of problems, lesson set 60